Okay, so with this problem, this is number 24, and I'm just going to be doing A and B because that's what my teacher wants me to do. So for that one, it says a spring of rest length L sub A with no tension, so it's a spring with no tension, is connected to a support at one end and has a mass M, big M, attached at the other. Neglect the mass of the spring, the dimension of the mass M, and assume that the motion is confined to a vertical plane. Also assume that the spring only stretches without bending, but it can swing in the plane. So essentially, we just have a pendulum. That's what we have. We have a spring pendulum. And so we'll go ahead and draw it so we can get all the details out of the way. So we have this thing, it's a spring, and when it's out here, doing its pendulum swings, it has this mass in the end, mass M. And so there's this angle here, just like a normal pendulum. There's this theta, and then the difference here is that this length is going to be LA, and then this, whatever this y direction, so we'll call it y direction happens to be, is going to be r cosine theta, and then this distance between it is going to be r, so we're going to call r whatever the actual distance that the spring is stretched to. So it's going to be LA plus whatever number, and that sum is going to be r. So this difference, when there's zero potential, is going to be r minus LA. So that's what this distance is. Yeah, for whatever potential. All right, so for our kinetic energy, we have, I did this in a previous problem. I'm not going to derive it again, but we have 1/2 m, and then we have r dot squared plus r squared theta dot squared, and that is just the polar coordinates for v squared. That's v squared in polar coordinates. So we derived that before. I'm not going to do it again. Then we have our potential is really just the sum of the spring potential with the gravitational potential due to the weight. So we have minus mg r cosine theta, and then we're adding the potential of the spring. So it's 1/2 k. This is where the potential matters. So that's where the m is oscillating up and down. So this is the r minus LA squared. So this is our y component, right? So this is our y component of the spring's oscillation, allowed oscillation, given the terms of the problem. So if that makes sense. So this is the y. This is the distance. This is a degree of freedom in the y direction that the spring is allowed to oscillate. So that is why we are putting that number there. So that is our v, this is our t. And with that, we'll get straight into writing our Lagrangian. And that is L equals, so we just have t minus u equals this 1/2 m r dot squared plus r squared theta dot squared minus a minus plus mgr cosine theta minus 1/2 k r minus LA squared. Okay, so that's our Lagrangian. Let's put a box around that, so it's important. All right, so now we're going to do our Euler-Lagrange equations. We'll start with r. So we have d dt partial L with respect to r dot minus partial L with respect to r equals 0. All right, and so first we'll do partial L with respect to r, and that is equal, so up here, where is r? So it's in a few different places, really. So we'll do the first one. So 1/2 says r squared. So it goes to 1m r theta dot squared plus mg cosine theta. And then this, we have our chain rule. So we have minus 2 times 1/2. We got a 1k minus k r minus LA times the derivative of r, which is 1. Okay, so this is this one. And then we have the partial L with of r dot, okay, with respect to r dot. And then r dot, where is that? There's only one term for r dot. That's good. So then we have 1m, because the 2, r dot. And yeah, and then we have, if we just add the time derivative, it's really easy. I'll just do that in one fell swoop. And that's mr double dot. Get rid of these stupid suggestions. It's always there. Okay. All right, so now we write down the full shebang, and that is mr double dot, subtracting all this, minus mr theta dot squared minus mg cosine theta plus k r minus la. Okay, so that is our first equation of motion. And let's go ahead and get our second one, which is d dt partial L with respect to theta dot minus partial L with respect to theta equals 0. And so going back to our equation up here, theta is only in one place. So we'll do partial L with respect to theta equals minus mgr sine theta. Okay, and that's it for that one, right? Yes, okay. Now, partial L with respect to theta dot. Where's the theta dot? There's just one. Okay, so that is 1 full m r squared theta dot. There's our angular momentum again. It's kind of a funny thing showing up. All right, but we need the time derivative of this guy. And it doesn't equal 0 anymore like the another problem we had earlier. So this, we have to do the full thing and do the chain rule. Why did that happen? Okay. So the chain rule makes this 2mr theta dot, okay, plus mr squared theta double dot. And now we have the two terms. Add them all together, put them in order, so we get mr squared theta double dot plus 2mr theta dot minus a minus plus mgr sine theta equals 0. And there's our second equation. Okay, so that's it for the first part. For the second part, what we need to do is some approximations. And so let's change color real quick. The approximations are specifically small angles. So that means like sine of theta equals theta, and then cosine of theta equals 1. And so we'll write our motion equations of motion again. So mr double dot minus mr theta dot squared plus k r minus LA. What was this? R minus LA. Oh yeah, minus, forgot the minus mg cosine theta equals 0. Just kind of circle these because we're going to work with them. So let's do the first one. So we can divide out everything on the first term. So there's a divide by m. And then we can get rid of this cosine. That goes to 1. Divide by the m. So divide by m, divide by m, divide by m, divide by m. So we'll rewrite that. R double dot minus r theta dot squared plus k, our good friend that we know and love, k over m, r minus LA, minus g equals 0. So this is our new equation for small angles. And then we'll do the same thing for our other one. Our other one is, what's our other one? Okay, it's mr squared. Let's write this. Mr squared theta double dot plus 2mr theta dot plus mgr sine theta equals 0. So this one will divide out mr squared, this, and then this sine of theta will just turn to theta. So this is theta double dot plus 2 over r theta dot. Is that correct? Yeah, that is. Okay. Plus g over r theta. Okay, is that right? Yeah, I think so. Okay, equals 0. Yes. Am I missing an r dot somewhere? I feel like I am missing an r dot. 2mr. Oh, yes, I am. This should have this term. I'm so sorry. This term should have an r dot because of the time derivative. I did this wrong. There should be a time derivative. Not here, but here. There should be a time derivative here of r. I'm so sorry. So that's where I messed up. So there should be an r dot here. Okay. Yep. Sorry about that. All right. So now this is good. And now what it wants us to do then is essentially for, what does it say? Let me read it. Also soon be solve these equations for small stretching and angular displacements. So what we do is we start with 0 displacement. 0 displacement means it's at equilibrium, meaning it is not moving at all. And if it's not moving at all, then we can set all of our time derivatives to 0. So anything that has a dot on it goes to 0. So I'm just going to, that's going to go to 0, that's going to go to 0, this is going to go to 0, this is going to go to 0. You see this? So that's going to give us new equations where we have k over m r minus LA minus g equals 0. And then we have theta equals 0, which makes sense. So, you know, at our initial conditions, if there's no movement at all, no displacement, then theta is going to be 0. So this makes sense with what we're trying to do here. Now what we do is we're going to set r to equal our r equilibrium position plus some displacement, some small displacement that we're going to call x. Okay, and so we're going to do that with our original equation. First, we're going to solve for r here. Let's do that first. So this, I forgot to do that. So we're getting gm over k plus LA, right? And that equals r. Yeah. That's this new equation of our equilibrium position. So this is our r equilibrium, okay? This is our r equilibrium. So now we have R, we're going to turn into R equilibrium plus X. And so let's just do that. So we have X equals R equilibrium. Oh, yeah. So X, we're solving for X here. So it equals R minus R equilibrium. And so when we have that, we're going to have, oh yeah, and then theta. Okay. So our X, we're going to have X double dot, and our original equation up here, we're going to substitute in our original equation up here. That's going to turn out X double dot minus R equilibrium plus X theta dot squared plus K over M R equilibrium plus X minus LA minus G equals 0. Okay? This is just the trick. This is what you do. So you start at equilibrium, then you're adding something, a small displacement, whatever that happens to be. All of your angles are going to be small. So when you're doing these estimates, if you have a small angle, a derivative of a small angle, times another small angle, then that's 0. So any products of small things are 0. So this is 0, and then also remember up here that this Km R minus LA minus G equals 0, we have that here. So everything except this X, this Kmx is going to go 0. So we have X double dot plus, so this is going to go, these are all going to 0 because of this equation we have up here. So K over M X equals 0. So X double dot equals minus Km over, oh, not Km, but K over M, K over M X, which looks familiar, should look familiar. All right, now our next one we have, so we'll just highlight that because this is important. All right, so our next one is theta double dot plus 2r dot theta dot over r plus g over r. This was our theta equation of motion. All right, so now we're just solving for theta double dot plus, this is a product of two small things, small radius, small theta, and so we're calling that 0. This is our estimation, 0, for very small oscillations. G over r theta equals 0. And then this r is our r in our equilibrium. So that's what this r is. So we're replacing the r in this equation with r equilibrium. And so now with our, so explicitly to write this out, we have theta double dot equals minus g over LA plus mg over k theta. Okay, so this is our other equation. And so what does this mean with this equation here and this equation here? When you solve them, you set k over m to be omega squared, or omega equals the square root of k over m. And this is our radial oscillation, see? Like a normal spring. This is our that's our frequency, okay? This is our angular frequency. And then this one here, omega sub theta, the frequency of that is g over LA, or whatever length, plus mg over k. And there you go. That's what we retrieved from doing our small estimations. I'm not going to do part C and above because the teacher didn't ask me to, but if anyone's watching this and wants me to do it, then I have no problem doing it. Just let me know. All right, thanks.